Hello, dear friends. In this video, we are going to see about transformer models in generative AI. Hope you have watched the other parts of generative AI so that you have little more understanding about this transformer models, where I have explained some of the basics of transformer models, basically like the transformer model used in language models and how it is working. So based on that base, here we are going to see how the transformer model is not only for text. It is also available for all other kinds of modalities like image, video, audio, code, whatever it can be. So for all kind of data types, we have different transformer models, and we are going to see how the transformer models is working for other data types as well. So you will understand it very well. So already we have learned in previous video what is generative AI. So we know that generative AI help us to generate new content like image, video, or audio, or code. It will understand the patterns, all these things. So it is powered. Actually, we know that generative AI is a model of deep learning, and the basic architecture behind this and the important architecture behind this generative AI is a transformer model. So this is what used in chatbots, image generation. So in all these voice assistants, in all these places, this transformer model is working. So it is like a backbone working behind this generative AI models. So let's understand one by one. So the transformer model is basically a neural network architecture introduced in the year 2017. The important thing behind this transformer model is the attention mechanism. So we have already saw what is attention mechanism, right? So it is using the important concept called self-attention mechanism. That is, it will find the important key tokens, and then it will find the relationship between them, so that it can able to understand the longer context, and it could able to give the better result. That is what the main objective behind this attention mechanism. And all this are processed in parallel so that we can have a better understanding and relationship between the elements, so that we can get a good or apt prediction of the next tokens or whatever it may be. So the basic idea of this transformer model is to find the important parts of the data and to find the relationship between the data based on that particular context. So why we want transformer model? As I told, the transformer model is like a backbone of all this generative model. So why this transformer model is important when compared to other model is, like, transformer model is very much better than this older models like RNN, LSTM, because it could able to understand the longer context. And the dependency on it. So it is also highly scalable, and as I said, it is the backbone of the modern AI system, that the generative AI. So there are many different types of transformer models are there in generative AI. So there is a transformer model for text, transformer model for image, transformer model for audio, video, code, and also for there is also transformer model for multimodal also. So let us discuss one by one so that you can understand how the transformer model is working not only for image, also how it is working for the other modalities. Let's go on by one. The first one is transformer model for text. So if you have watched my previous video, we have discussed the same there as well. Like it is like processing our human natural language. So what happen here is, whenever we give a input prompt, a sentence, it will be divided or tokenized into splitted into so many tokens. And these tokens will be converted into a numerical representation. That is what we call it as embedding. So this, because all the tokens are in the form of embedding, understanding the meaning and the semantic, okay, is very easy. Since all in the numerical format, and the working is very easy for the transformer model. And what is the application of this is like chatbot, translation, text generation, in all these places. This is how it is working. So the example for text transformers are ChatGPT, GPT-4, all these are examples of text transformer. So how it is working? Whenever we give a prompt or input a human language, That prompt the text, the longest sentence is converted into tokens that we call it as tokenization. And the important mechanism behind this transformer model is self-attention. What is self-attention? It will find the important words and it's in the particular context of the given input, and it will find the relationship between the important words in longer context so that it could able to capture the relationship. Since it knows the context very well with good understanding by finding the relationship between the tokens, it could able to find a better apt next word, by which it will be doing it again and again. So it is an auto-regressive process. It will be iteratively happening again and again. By that, it will predict the next word in a sentence. So when we saw, we can find that it is giving the output at a stretch and giving answer. But actually, what is happening behind is this. It will be predicting the token by token in this manner. So that's what about transformer, and that's how it is functioning. So let's go to the next transformer, the transformer model for the image. So remember, transformer model is also a neural network architecture. So let us see how that is working here is, like here the input is image. So what happens is this image is splitted into small patches. Like when we give text as an input, we divide the text into small tokens. For example, when I say artificial intelligence is changing the world, so artificial is a token, intelligence is a token, is this a token, changing is a token, world is a token. So that's how the token will be happening in the text. But what happened in the image is, you consider this is my original image. So this image is splitted into small patches. You can see here, so this small square boxes. So this is how this small square boxes is called patches. So this is how it is, like tokens in the text, we have patches here as tokens, and then this is processed using attention. So what is the applications of image transformer is, in image classification, image generation, object detection, in all these places image transformer is used. An example model or a transformer model for images, VIT, that is Vision Transformer, DALI, all these are example for image transformer. So here even we can able to convert a text into image as well. So that we'll be seeing in the end. And so what is this patches? I told it's a small piece of image. Instead of looking it as a whole image, the transformer will be splitting into small part. We call it as patches. So the small square boxes. So that square is like a word in the sentence. So here we can see little more about its functionality. So what is the step when we give a input image? It is splitted. So you can see the red color lines. So it's splitted into small patches. And then let us see this part. No, this is zoomed here. So what has actually happened here is, the every single small boxes, that is called patches, is now flattened into, say, this is like a small patch, right? So that is flattened. How does it is flattened means? So this, like, so we, for every small patches we have the width and the height, no, and also the number of channels. So that together is converted into a one-dimensional vector. So it has the height information, weight information, followed by the three channel. What is three channel means? If it is a color image, we have three channel. So this small patch is now converted into 1D vector, that is flattened into in this format. So and then it will be converted by with the help of numbers, right? So this is converted like this in the form of, and each patch is represented in the form of numbers, and this numbers is converted into embeddings. How so this will be this, no, this 1D array, this flattened vector is given to the dense layer. So the dense layer convert all these things to a embedding. So we know already what is an embedding, numerical representation. So all the embeddings will have a certain equal size. So likewise, it is converted into embedding. So, but likewise, for every small boxes, it is converted into this numerical format that we call as embedding. Then this embedding is now fed into the transformer. Then, as usual, the things will be happening. So this process was explained here. The wolf image sizes height into width. So this red box, each small red box, and this original image may be of size 256 cross 256, and now each it can be converted into 16 cross 16 patches, and then each patches will be represented in this format, by which it is flattened, and then the flatten is a given that is a 1D one dimension vector, and then this flattened one dimension vectors is given to the dense layer, and the dense layer will convert this flattened data into embeddings. So embeddings is like this. So final that embeddings is given into the transformer. Okay, so this is how it will be working. So if you have a image, so that image will be having many patches, and all the patches will be having its numerical representation that is fed into the transformer. So that is what actually happening. So if you want to understand, patch means small part of the image, flatten means converting that particular, here you can see, converting that particular patch into the one dimension vector, and this one dimension vector when passed to the dense layer. So here the vector is passed to the dense layer, that is fully connected layer. It convert it into fixed size vector. This is what the fixed size vector, we call it as an embedding. So that is a numerical representation. So this patch is the token for the transformer now. The patch representation for the transformer. So this is how it will be working. So I hope you can understand how actually the transformer models are understanding the images. Now let's go to the audio transformer. So audio, we'll see how audio transformer is working means here in image, the images are split into small patches. In text, that is converted into small tokens. Similarly, here in the audio is converted into so many spectrograms. So which means the image representation of that frequency, the audio, and then it will be processing. So let's see that. So what is the application of audio transformer in speech recognition, voice assistant, audio generation? In all these places, audio transformer is used. The example is one of the example model for audio transformer is whisper. So here it is converting the speech into text. So here is an example. So we have whenever we speak that audio, no, so it is converted into a visual representation of the sound. Here is an example. So instead of directly using the audio, the raw audio, it is converted into something like an image like this. So the sound waves. So this sound waves in the form of time, frequency, image. So we have the x-axis represents the time, y-axis represents the frequency, and the color intensity specifies the loudness of the image. So the audio image is now in the form of the audio signal is now in the form of image. So why we are converting this audio into this kind of spectrogram? This is called a spectrogram, the visual representation of a sound. The reason behind that is because the transformer model cannot directly understand the raw sound voice. So that we are converting it into like a 2D format, like an image. Now the transformer model can process it like the image. So image will be converted into small patches. Then as like then it is processed. How in image we have patches, text we have tokens. So similarly. So let us see the working principle behind this. So whenever we have a speech or a audio, that is what audio can be, a music or a speech or whatever it may be, that is converted into spectrogram, the visual representation of the sound. That is 2D representation. It's look like an image. Now, as usual, if it is an image, then it is divided into small segment, as we saw here, small segment. So this small segment is the called as patches. This is the small segment, right? So similarly here also it is divided into small segment. We call it as image patches. So here the spectrogram is divided into small blocks. We call it as time, frequency, chunk. We call it here as chunk. So these are like audio patches. So in image we use patches. So here we can call it as audio patches. So we know this next step after getting the patches, flatten it. And then it become a one dimension. So then after this one dimension vector, we convert it into embedding so that we have a fixed size of the numerical format. So that we get because this one dimension flatter data is given to the fully connected dense layer, then that will give us a fixed size embedding, the numerical representation. So each that is called as chunk. Each this image patches, no, that the time frequency chunk is a token now. So that the embedding actually. The embedding is now fed into the transformer. So now it can able to process same thing. All the transformer model, the we have an attention mechanism. So that's how it understand the relationship between every tokens or the chunks, and that it could able to produce the output. So the model learns which sound is mattered, what is the speech pattern behind it, what is the context behind it, all these things. So now we can summarize it. So text means we have tokens, that's a word. Image means we use patches. So here in audio we use spectrogram chunks. That is the small division, that small black. Thus in the image we have the patches. So same thing. So that's how the audio transformer is working. So the next one is a video transformer. So till now we know what is audio. That's all okay. But video means how it is working means video means we know it is a sequence of frame. So we can simply say it is a sequence of images like that. So what does it learn from this means? It learns the spatial features. And the temporal features. What is the spatial space related? The information within the frame. So as I said, video means it's a sequence of frames or sequence of images. So it should understand two things. One is it should understand the information within the frame, like an image, and then it should find the information across the image. That is called as temporal feature. So these two important features this transformer model will be learning about. So that we'll discuss. So what is the application of this video transformer is video generation, action recognition. So what is actually happening in this video? If you ask some query, it should able to reply back, right? So it could understand what is happening inside. It could able to summarize the happening in the video. So all these things are the application which could be possible because of this video transformer. So the video transformer tracks what is actually happening in each frame, how it is changing over time, all these things. So that is very important. So you should understand each frame. Also it should understand what transformation is happening in each frame, what is transforming. So that is what is changing over time. So a video is nothing but a sequence of images, so frames over time. So the transformer should process each image, each frame, that is an image, like an image patches, and then it should also understand across the frames, right? So it is like sequence of frames over time. Also, it should understand. So let's see how it is, like how spatial features and how temporal feature is working. So spatial features means what? As I said, video means it is a sequence of frames. So first it should understand one frame, then it should understand the changes in the next frame. So in within a frame means it is a spatial features. So it is like a single image. So each image, then we know if it is an image, what happens already we saw, no? The image will be divided into small patches, and that is flattened, then it is embedded. So then give to the video vision transformer. So that's what actual procedures and the what model learn. So when it see that particular frame, it could understand what are the objects are there, what are the colors, what are the shapes there. Like objects means dogs are there, a person is there, or a car are there. There is whether is it contains buildings. So all kind of objects can be understood. Position where it is placed. All this information about a single frame is understood from that particular single frame. So example is from a frame, it shows a dog means it can understand about its ears, face, body. So this is the spatial information. So simply saying facial information means it's the information about a single frame, like a single image patch. The next one is temporal features. So this is the features across the frame, from one frame to the next frame. So understanding how things are changing over time. So from one frame, maybe the dog is sitting. The next frame, the dog may be standing. In the next frame, the dog may be running. So this transformation should be understood. So that is the changes over time. So the transformer could able to connect all these frames. So that is the speciality. So what the models will learn in this temporal features, it will understand the motion, what is the activity happen over there, like what are the sequence of event happen from one frame to the other frame. For example, if a person raised his hand, means next he would have waved his hand. So when a ball is moving, means which direction the ball is moving. So in one frame, the ball started moving. So next frame, in which direction the ball moving, in which speed the ball is moving. So this information are all collectively said to be as temporal understanding. So simply saying changes between the frames over time. So what is the working flow of this video transformer means? So first the video is splitted into frames. Each frame will be splitted into patches. We know then the patches will be converted into embeddings. That is the spatial information. Then frames. So we have a collection of frames now when it is a temporal informations. So we have so the frame sequence will be there. So the transformer, after we find this spatial information and temporal information, the transformer will apply the attention towards both the things. So it should apply attention within the frame. Also, it should apply the attention across the frame. So, like what you see in one scene, and you have to that is the spatial information. Temporal means what is the progression on the next frame. So both together will give us the full understanding about the video. So what is inside the frame, what happened over the time in the next frame. So the transformer combined both the things together so that you could able to understand the video. That's how the video transformer is working. So it's interesting, right? So the next one is code transformer. So we know that nowadays code generation became much easier because of this transformer models. So how this is working means the code transformer is going to treat the code as a structured language. It will understand the syntax and the logic behind that. Something similar to text. So what are the applications of this code transformer is code generation, debugging, auto completion of a code, all these things. The model behind this code transformer is GitHub, Copilot, Codex. All these are examples of code transformers. So how the code transformer treat code in the sentence we have words, image we have patch, audio we have chunks. Here in the code we have tokens. What is tokens means? Here the smallest meaningful part of the code. Here is an example. You consider here we have a for loop. So what are the tokens? Everything is a token. For is a token, I is a token, in is a token, range is a token, open parenthesis is a token, phi is a token, close parenthesis is a token, colon is a token, print is a token. Likewise, each and every small parts are taken as tokens. So that was the smallest part of code. As in image, we have patches, no? And then in text, we have words, no? And in audio, we have chunks. Similarly, here we have this tokens. And then, so let's see the working flow of this code transformer. When we have an input code like a equal to b plus c, so we will be converting into tokens, right? So a is a token, equal to is a token, b is a token, plus is a token, like that. And then once we got the token, as usual procedure, convert it into numerical form. That is the call, we call it as embedding. So for example, for a, the embedding, the numerical representation is this. It's continuing. Okay, it may be of different size, 865 numbers may be there, it depends. And here is small example, and then for equal, this is the numerical format, same as text transformer. After we get the embeddings, that is the numerical representation for each and every tokens, then we apply the attention means we have heard it many times, right? It finds the relationship between every tokens. So for example, in this example, we understand a has a relationship between b and c, which means a is depending on B and C, and the plus is an operator which connects B and C. So it learned the logics behind it, and also it learns the dependencies. Finally, it generates the output. So the code model can able to complete the code, it can able to fix the code, it can able to generate new code as well, because it can understand the logics, the dependencies between the tokens of the code clearly, so that it can understand the syntax, everything, so that it could able to complete the code, fix the errors and all these things. So why does it learn what is actually learned in the code? Like unlike text, here we have strict rules, because all the programming language follows certain rules, Python or C or Java, whatever it may be. So it should understand the syntax. What is the grammar used for the code? What is the semantic of it? What is the dependency between the variables? All these things should be understand. For example, when I have x equal to y plus c, so x is depending on y and z. All this kind of understanding should be there. This is the attention in the code. So as shortly we can say, code transformer break the code into tokens. It will understand the relationship between attention models, and it will generate or understand the code as human developers. So this is a small summary of what we learned, the different kind of data types, and how the transformer, what is the transformer's input. So text means the input is a word, image means patches, audio means a spectrogram chunk, and video means frames as well as the patches. Code means tokens. Final transformer is multimodal. So here we combine multiple data types. So until now we worked with the text alone, video alone, image alone, and code alone. Now we can have a combination of these data types. For example, text plus image. So together we can work on it. For example, we can able to describe an image. So we have an image as well as the text, right? So both kind of data types or modalities are there. So it could able to generate content from mixed input. So here you have the, like, these are the different modalities like text, image, audio, video. So one of the example for this multimodal is GPT-v4. So it can understand both the text as well as the images. So instead of handling one particular type, it could able to handle multiple data types together. So here is an example. So let us consider here we have given a image as well as a text as an input. So we are giving an image of a dog as well as we are going to ask a question, what is this animal doing? So here we convert each modalities into tokens. For example, already we know so both, like, image is processed separately, text is processed separately. So image means we have patches, text means we have tokens. So if it is an audio, we have chunks. So now everything is in the same format. So because you know that the process already we have discussed, no, text also finally divided into tokens. Finally, we get an embeddings. Here also image also we have, we convert patches. Finally, we have embeddings. So for all together we have embeddings for all. So so all these things are considered together. So all the modalities like are shared. So information about the image as well as the information about the text are all in the embedding format, so that together are considered. So they both are considered together, are merged together. So tokens are merged in a single sequence. So then we'll be applying the attention mechanisms. So then it finds the relationship between what is the image contain and what is the text asking about. So it could able, so because already we know attention means it will be finding the relationship between the important things, so that it could able to understand. So the word dog attends to the dog image part. So in the question I am asking what is animal doing, so it can understand what is the animal doing. So it can understand the word dog and attends to, okay, so then it will connect both. So it could able to answer the question, describe the image. It could able to generate the caption. It could able to make a summary about the image, whatever it may be. So these two more modalities are converted into embeddings. Both are considered together, and applying the attention model, we'll get the output. So this is the workflow of it. So multimodal transformer means where input can be a text plus image, text plus audio, text plus video, whatever it may be. So then it will be converted to tokens, embedded into vectors, that is the embedding. And then we combine the sequence, maybe text embedding as well as the video embedding. And then we apply it with the attention mechanism across the modalities, which means text as well as the image. And then we create the output. So this is how this multi-model model will be working. So example is GPT v4 and the click. So multi-model transform model converts the different data types into tokens and then combine them and then use the attention model to understand the relationship between among the modalities. So this is a summary of everything. So everything is actually converted into token. Text means words are tokens. Image means patches. Audio means spectrogram chunks. Video means frame as well as the patches, because it should understand the spatial information, also the temporal information. So I hope you got the clear understanding about how the transformer model are used in different modalities and how it is working. Thank you for listening. God bless you, Ma. Thank you.